Okay, the quiz for this class was first add 2/3 plus 3/8 times 1/2 plus 1/4. And you have to follow the order of operations. My camera doesn't seem to, okay, that a little blur. Okay. 3 and 8 have common denominator, 24. So you would start this by saying 2/3 multiplied by 8/8 plus 3/8 multiplied by 3/3. So that I've just multiplied 2/3 by 1 essentially, but I'm going to change the form of it. And then that's times 1/2 plus 1/4. Now I'm not going to go through the details of this. I'm just going to say you get 16 for the numerator here, you get 9 for the numerator here. The denominator in both cases is 24. So you got 16 24ths plus 9 24ths. How many 24ths do you have? 16 and 9. 16 and 9 makes 25. So this gives you 25 24ths. You multiply that by 1/2. Well, 25 over 24 times 1/2. You can write this down if you like. 25 over 24 plus 1/2. You multiply the numerators. Numerators are 25 times 1, which gives you 25, and 16 times 2, which is 32. So you get 25 over 32. Now, you do that multiplication by 1/2 before you add the 1/4 because of the order of operations. You do what's in the parentheses to get your 25 over 16. You multiply by the 1/2 to get your 25 over 32. And then you add 1/4. Now you're going to have to find a common denominator there, but 32 will be your common denominator. You're going to get 8 over 32, and I think you're then going to end up with 33 over 32. Figure it out for yourself. That's, you really need to understand that thoroughly. Because that's basically elementary school arithmetic. However, people don't know the elementary school arithmetic when they get to college because they've done everything on the calculator. And you're going to need to know it. I keep emphasizing you need to know how to operate on fractions because you're going to have fractions with symbols not too far into the course, about halfway through. So you really have to understand that. Okay, what's the domain of y equals f of x equals square root of 5x plus 12? Well, just briefly, of x plus 12 can't be negative. Has to be greater than 0. So you're going to get x is greater than or equal, has to be greater than equal to 0, greater than equal to negative 12/5. I'm writing that small because I don't have a class out there. And you can see that on your screen. That would be the interval then from negative 12/5 to infinity. So we could write that as the interval negative 12/5 infinity. Having been through the assignment, that should be pretty clear. The hurdle here is understanding that whatever's under the radical sign has to be non-negative, meaning it has to be at least 0, greater than or equal to 0. You set that up, you solve for x. Hopefully it's an easy expression to solve for x, this is. Then you write that as an interval. Okay, then we've got f of x equal quantity x minus 2 squared plus 5. What's f of 6? Well, x has become 6, so x here has to become 6, and you get 6 minus 2 squared plus 5. And I'm not going to write out the details. 6 minus 2 is 4. You square that, you get 16. And this equals 21. You can verify that. I do make mistakes. Okay, what's f of 8 minus f of 6? Now, people will often kind of think like a distributive law, like factoring out on f, but f is not a number. It's not a symbol for a number. It's not a variable. It's the name of a function. So you can't factor out the f. You don't get f of 8 minus 6. We'll evaluate that just to contrast with this, but it's f of 8 minus f of 6. Now, f of x is square root of 5x plus 12. Well, that's the square root of 5 times 8 plus 12, maybe a little hard to read, minus the square root of 5 times 6 plus 12. Now that's approximately equal. This is like 52, so that's like 7.3. Square root of 52 is about 7.3. And you can use your calculator to do that, but 7 squared is 49. So 52 is a little more than 49, between 49 and 64. That should be between 7.2 and 7.3. The calculator will give you a more accurate result. And 5 times 6 is 30, and you add 12, you get 42. And the square root of 42 is between 36 and 49. It's around 6.5. So that equals approximately 1.8. This does equal 1.8, but it's an approximate value of this because you got this approximation here. These numbers are approximations. This is equal to this, but it's an approximation of all this. Okay. Again, check me. I'm not infallible. F of 8 minus 6. That's not f of 8 minus f of 6. In the parentheses, you got 8 minus 6. That's f of 2, which equals square root of 5 times 2 plus 12. 5 times 2 is 10, 12 gives you 22, and the square root of 22 is about 4.7, I think. Okay. Then again, check my arithmetic. But this is how it's calculated. You subtract the 6 from the 8. In this case, you don't subtract the 6 from the 8 in this case, because f is not a number, doesn't represent a number. It's not a variable. You can't factor it that way. Okay. Now what's f of z plus 2? Well, f of x is a square root of 5x plus 12. I'm sorry, that was up here. Oh man, I was doing the wrong f of x. Well, I did these for this f of x. So I'm going to say if f of x equals this, we'll evaluate these. I really intended to evaluate this function, but you can do that. Okay. I'm going to change back to this function, but I've got to write that out, so that mislead. If f of x is your x minus 3, it's x minus 2 squared plus 5. Then what's f of z plus 1? Okay. You don't want to think too much about this. X becomes z plus 1. And if x is z plus 1, then f of x equals x minus 2 squared plus 5 becomes f of z plus 1 equals quantity z plus 1 minus 2 squared plus 5. X has been replaced by z plus 1. Now, we want to simplify this a little bit. Z plus 1 minus 2 is just Z minus 1. So you got Z minus 1 squared plus 5. And we can expand the Z minus 1 squared. Now, Z minus 1 squared is not Z squared minus 1 squared. Okay, it's Z squared minus 2Z plus 1. And you should understand that by the distributive law. But we'll talk about that shortly when it becomes really relevant. Anyhow, this simplifies to Z squared minus 2Z plus 6. Now, I've mentioned distributive law, so I'm going to do this quickly. Z minus 1 times Z minus 1 equals what? It equals Z times Z minus 1 times Z minus 1. I multiply Z minus 1 by something, I multiply Z by that something, and then minus 1 by that something. And that equals Z squared minus Z minus the quantity Z minus 1. Of course, 1 times Z minus 1 is just Z minus 1. And that equals Z squared minus Z plus 1. Is minus Z minus 1 is minus Z minus 1, which is plus 1. And that equals Z squared minus 2Z plus 1. I throw that in because that ought to jog your memory a little bit about something you might well have forgotten if it's been a few years since you had a math course. Okay. Now, the thing I want to do next, and I've actually preserved it from when I did this without sound accidentally, the same function, f of x equals quantity, very similar function, it's not the same function. It's now x minus 3 squared plus 5. Very similar to the function I just did, okay? We want to find the average rate of change of y equals f of x with respect to x on the interval from 2 to 5. What in the world does that mean? It means we calculate the change in y divided by the change in x. This is an interval of the x-axis, so the change in y occurs between x equals 2 and x equals 5. The change in x is change from 2 to 5. That changes by 3. Okay, the calculation. Evaluate f of x at 5. Okay, evaluate it at 2. And you get the change in y, because y equals f of x. Okay. The change in x, where we're changing from 2 to 5, the change is 5 minus 2, which is 3. F of 5 is easily calculated. You plug 5 in for x. Now, hopefully you've digested what we did previously in the quiz, and you understand function notation well enough to see what's going on. Again, f of 5 means x gets replaced by 5 everywhere in this, on both sides of this equal sign. And you get quantity 5 minus 3 squared, and you have 5. And then f of 2, x becomes 2, and you get 2 minus 3 quantity squared plus 5. And you do the arithmetic, you get 9 minus 6 over 5 minus 2. And that's 3 over 3, which is 1. So that's the average rate of change. Now, there's a way of representing this on a graph. The interval 2, 5 means the interval from x equals 2 to x equals 5 with closed dots on the end to indicate that you're including 2 and 5 in the domain. Okay. The values of x are the values that we just calculated. F of 2 is 6. Again, put 2 in here and evaluate it. Okay, you're going to get 6. F of 5 is 9. Put 5 in here, you're going to get 9. So we have y equals f of 2 equals 6 on this line. Y equals f of 5 equals 9 on this line. when x equals 2, y equals f of 2, which is 6. So we take the vertical line from x equals 2 and it intersects the line where y equals 6. And then we take the vertical line from x equals 5 to where y equals f of 5, which is 9. And we put a point there. Then we sketch this right triangle as we did in the previous class. We have a run from here to here. And I like to put arrows in this. We go from the leftmost point to the rightmost. See, this arrow goes here and this arrow goes here. Now, if we follow the arrows, we have a path that takes us from this point to this point. Okay, from here to here, and then to here. The direct route from this point to this point is the hypotenuse of the triangle formed by these two arrows. This arrow runs from x equals 2 to 5, so the run is 5 minus 2, which is 3. This arrow goes from y equals 6 to y equals 9, so the rise is 9 minus 6 equals 3. So the slope is rise divided by run, which is 3 divided by 3, which is 1. Now, the slope is 1, average rate of change is 1. What's this foolishness comment here is no longer relevant. But there we have the average rate of change of this function with respect to x on the interval from 2 to 5. And important comment, the slope and the average rate of change will have the same numerical value. If you have units on y and units on x, as we've seen before, you include the units in the rise and the run, and you get this unit divided by that unit, like dollars over hours in a previous example. Or you could be miles over hours. If you're traveling, know how many miles, how many hours you get, how many miles over hours, which is miles per hour. Many, many, many other examples. Very important for understanding both graphs, calculus, applications. So average rate of change is a big deal. Okay, now the next topic we want to take up is toolkit functions. Okay, that'd be y equals x squared, y equals 2 to the x, y equals x cubed, y equals 1 over x, y equals 1 over x squared, y equals absolute value of x. Call this the quadratic or squaring toolkit function. Call this the toolkit exponential function. Call this the toolkit cubing function. This is a toolkit reciprocal. X, you're doing the reciprocal of x, reciprocal function. This is reciprocal square. You do reciprocal of the square. This is the absolute value. We want to look at graphs of these functions and understand some of the behavior of the functions. And first place, we want to understand how to calculate the values of these functions. So starting with y equals x squared, we make a table. Now, if you're in my section, we've constructed these functions within a window by doing some halving, some subdividing. Other classes haven't, so I'm not going to do that here. But generally, the numbers I use, and if you're in my class, you kind of understand why. -2, -1, -1/2, 0, 1/2, 1, 2. Okay, you try to use all these numbers. Now, for some functions, for example, 2 to the x, 2 to the 1/2 power, you have to use a calculator or expand a power series, which is something you don't learn until second semester calculus. So you can't do that. You can use a calculator, but that doesn't give you any information. That doesn't help you understand the function at all. It just gives you numbers, meaningless numbers. So we need to be able to calculate this, but we would leave out -1/2 because we can't calculate 2 to the -1/2 in any way that you would understand. other than punching it into a calculator, which is not calculating at all. Okay? Y equals x cubed, we can evaluate these and do, and 1 over x. Well, 1 over x can't be evaluated when x is 0 because division by 0 is not defined. As I've explained, that can be understood very simply. If you count by twos, you get 2, 4, 6, 8, 10. So 10 is 5 twos, 10 divided by 2, then is 5. If you want to divide 10 by 0, you count by zeros. 0 and 0 is 0. 0 is 0 and 0 is 0. You're never going to get anything but 0. You're never going to get 10. You can't divide 10 by 0 in any meaningful way. So we say, when we get to this one, we don't bother with 0, but we use -1/2 and the 1/2 and all that. Similarly for this function, because if x is 0, you still have 0 in the denominator. And then there's the absolute value, which may be the easiest function to understand if you understand it. Okay. So we want to evaluate y for x equals -2. Well, we get -2 squared because y equals x squared. X is -2. In that case, y is the square of -2. Now that equals -2 times -2, which is 4. Make a comment down here. -2 squared is -4. Because of the order of operations, you square the 2 before you apply the negative. If you want to square -2, you'd better put it in parentheses. Now, some calculators, if you put this in, will tell you it's 4 because they're not respecting the rules of arithmetic and confusing the issue. Excel does something very similar, okay? You put this in without parentheses, and I think Excel will still give you a -4. It's because Excel wasn't written by mathematicians. Okay. If you square -2, square the quantity, this means -2 times -2, which is 4, and that's what you get when you square -2. So don't be putting -4. I see a lot of that. Okay. So try not to do that. -1 squared, which we have to write this way. We don't write it with a negative and a 1 squared. I'm going to have the parentheses. Don't write this. Okay. Well, that equals -1 times -1, which is 1. -1/2 squared is -1/2 times -1/2. Well, the negative times the negative gives us a positive. We multiply the numerators to get 1. We multiply the denominators to get 4. So that's 1/4. 0 squared is 0. 0 times 0 is 0. 1/2 squared is, again, 1/4. It's just like -1/2 times -1/2, but it's positive 1/2 times positive 1/2, which is certainly 1/4. 1 squared, well, I believe we understand that, is 1, and 2 squared, we understand, is 4. So right there is a table for y equals x squared between -2 and 2. Now, as you see in the course, as it goes on, these toolkit functions are used to build other functions. For example, y equals 2 raised to the -x squared combines this function with this function in a way that we're going to talk about pretty shortly, okay? And gives you 2 to the -x squared. You choose to put that negative there. And the reason you do that is gives you a good old bell-shaped curve. So that's where the bell-shaped curve comes from, just combining this toolkit function with this toolkit function in a specific way. Now, the standard bell-shaped curve actually involves e to the -x squared, and it's e to the -x squared over 2, and you normalize that by dividing by 2 pi, square root of 2 pi. But That takes a few steps to understand. You first got to understand the number e. So we start by understanding 2 to the x. All right. Well, next thing we want to do is probably make graphs of some of these functions. And since we've already made the table for x squared, we'll go ahead and make a graph for x squared. We move the camera a little bit more, too much back. Okay. Okay, if we want to graph this, now I'm going to choose to graph this in a window from -2 to 2. Because if you graph something on a calculator, you get a window. You graph it on a computer, you get a window. You can zoom in on the window, you can zoom out. You're familiar with all that because that's how you've done most of your graphing, most likely. Okay, so we have the line, vertical line x equals -2, the vertical line x equals 2. It's because we're going from -2 to 2, and that'll be our domain. We have y values that go from 0 to 4. Well, we generally want to have y equals 0, even if y equals 0 isn't in the domain. So we're going to include y equals 0, and we might as well go up to y equals 4, and we don't need any bigger window. So if you do what people are in the habit of often doing, is you go, here's -10, here's 10, here's 10 marks, and then you put 10 marks up here, and your graph ends up being in this little tiny window here, and you can't even see it. Okay, so you don't automatically make a table from -10 to 10. You could make a set of coordinate axes from -3 to 3, -2 to 2 would fit in that pretty nicely. And you don't need to go from 0 to 10 here. 0 to 4 suffices for this table. Now, the function can be graphed in a much bigger window. You graph it from -10 to 10. You'd have to go up to 100 here, which means you couldn't have the same vertical scale as the horizontal scale. So if you went up to 100, make the graph of reasonable size, you'd probably put y equals 100 here. And if you did, you would get almost exactly the same shape that you get here. Incidentally, by going to 100, this square shape would become flattened out quite a bit. Okay, well, you don't need all that information, but just a little perspective of why I like to graph in windows. I don't mean in PC windows, computer window, Microsoft Windows. Anyhow, we can put x equals 0 halfway between -2 and 2. And then we need x equals -1 and 1. Well, x equals -1. I would do that, forget that negative. My hand forgets, my mind remembers, but my hand doesn't necessarily follow my mind. Okay, now that's pretty poorly written on the left. See if I've got a little bit of damp cloth here to smudge it out with. That's pretty neat. X equals -1. Okay, it's still not great. Okay, then I also want x equals -1/2, which is halfway between -1 and 0, and x equals 1/2. Now, if you follow this procedure for dividing up the interval from x equals -2 to 2, go halfway and see what you got, then go halfway from there to there, and halfway from there to there, and then halfway from there to there, and halfway from there to there, you get a well-scaled graph. I often see people we'd write -2, -1, -1/2, 0, 1/2, 1, 2. So that the distance from 1/2 to 0 is the same as the distance from 1 to 2. No, that's only half the distance. So this is not right. So we cross this out. If we get the chalkboard. Okay, we don't do that. I like subdividing these intervals so that we don't get poorly constructed graphs, distorted graphs that don't look like they should. Okay. Now, the y values that we're going to need are 4. Okay, and then we're going to need 1. Now, where's 1 on the scale between 0 and 4? It's going to be about down here. Let's just be careful. Let's divide the interval from y equals 4 to 0. And put y equals 2 here. Then we can go halfway from 0 to 2. Here we get y equals 1. And halfway from 0 to 1 is y equals 1/2. We need 1/4. So that would be like here, y equals 1/4. Now, if we locate our points, -2, 4 goes here. -1, 1, -1, 1. X equals -1 on this line, y equals 1 on this line. There's our point. -1/2, 1/4. Well, here's x equals -1/2, and here's y equals 1/4. So that gives us a point all the way down here. 0, 0 is pretty easy. That's on the y equals 0 and the x equals 0 line. And then we get 1/2, 1/4, 1, 1, and 2, 4. Graphed by similar method. And if you do that, you get a graph that looks like this. I kind of missed that point. That line is kind of too far over anyhow. Okay, you get a nice parabola. If you, the better you draw this, the nicer your parabola. Doesn't take long to construct this. Now my class will understand how this construction is the same as the construction that we used for the squared function. Start at the upper left-hand corner, go over one line, down 2, over 1, down 2, over 1. And then we got to go down 2, so I would have to put the 1/8 line in there. Nobody else needs to know that. I want my students to understand these shapes and these graphs very well because they're just central to the course. Okay, so there is the graph, anyhow, of x squared in this window. Now, open math is probably going to tell you to use a calculator to evaluate it. I recommend that you ignore that. You need to understand the numbers. You need to understand the arithmetic in order to understand the functions. But if you're not in my class, you have choice. Or if you're in a class where that's not required, you have a choice. I don't know for sure what other classes are required. Got a pretty good idea. But not for me to dictate what the other classes do. Every instructor has their own perspective. And every instructor at this school at least deserves complete respect in those decisions. Okay. Well, we could do some of the other graphs, and I think we will look at the table for y equals 2 to the x. Okay, actually, looking at the original video, I don't think I did the 2 to the x function, but I'm going to do it briefly anyhow, because you need to know how to calculate these. At least I think you need to know how to calculate these to understand them well, and I believe your instructors want you to be able to calculate them too without punching buttons. For these simple values, okay? If x equals -2, y to the 2 to the x equals 2 to the -2. 2 to the negative 2 is 1 over 2 squared, which is 1/4, because you have the rule for exponents. A to the negative b equals 1 over a to the b for any number a except 0, because you can't do the denominator. Okay? And that rule makes abundant sense. I often write this sequence of numbers down, so I'll do it real quickly. 2 to the third is 8, 2 to the second is 4, 2 to the first is 2, 2 to the 0 equals what? 2 to the negative 1 equals what? 2 to the negative 2 equals what? This is sufficient to give you the idea. The exponents go 3, 2, 1, and you can't argue with these. 2 times 2 times 2 is 8, 2 times 2 is 4, just plain old 2 is 2. What's 2 to the 0? Now you've had this rule, any number to the 0 power is 1, but 90% of people come into pre-calculus thinking it's 0. Not sure how that happens, but somebody's, the curriculum is not doing a good job with that whole idea. However, it's easy to understand. Each of these numbers is half the one before. 2 is half of 4, 4 is half of 8. You certainly have enough arithmetic to see that very easily. You go up to 2 to the 4th equals 16. You go as high as you want. Now coming down this way, half of 16 is 8, half of 8 is 4, half of 4 is 2, half of 2 is 1. That's why 2 to the, I won't say that's why 2 to the 0 is 1, but that's one good argument to convince people that it's so. There are many other reasons it needs to be 1. Well, okay, well, now what's 2 to the negative 1? If you divide 1 by 2, you get 1/2. If you divide that by 2, you get 1/4. Now 1/2 is just 1 over 2 to the 1, so the a to the negative b equals 1 over a to the b. 2 to the negative 1 is 1 over 2 to the 1. 1/4 is, of course, 1 over 2 squared. So 2 to the negative 2 is 1 over 2 squared, which is 1/4. It's also 1/4 because it needs to be 1/2 of 2 to the negative 1. Okay. In any case, 2 to the negative 1 is 1 over 2 to the 1, which is 1/2. 2 to the 0 has to be 1. Just showing you a good plausibility argument here, why it needs to be so. 2 to the 1 equals 2, and 2 to the second equals 4. Now I can sketch the graph of this function on this very set of, on this very grid that I've created for the squaring function. Okay, I need -2, 1/4. Well, here's x equals -2, and here's y equals 1/4. So we have a point here. At -1, I should get 1/2. Well, x is -1. Here's the line y equals 1/2. That's going to give me a point here. 2 to the 0 equals 1. So when x equals 0, which it does on this vertical line, y equals 1. 2 to the 1 equals 2. Well, here's x equals 1, and here's y equals 2. There's a point. And 2 to the second equals 4. X equals 2, y equals 4. End up in that upper right-hand corner again. And we get this nice graceful curve with more detail possible. Okay, I don't include x equals 1, the point for x equals -1/2 or x equals 1/2, because you can't write it out as a decimal number accurately. You can write it out pretty accurately, but not exactly. Okay, you write it out to 48 decimal places or 48,000 decimal places, but it's never going to be exact. So I don't include it. It's not needed. The trend of this graph is so obvious that we don't need to use -1/2 and +1/2. You'd have to use a calculator, and even then you'd have an approximation. The other thing I will notice, though, if we were to go to 3, you would have, or to -3, you'd have 2 to the -3, wouldn't you? That would be 1/8. So every time you go 1 to the left, if you think about this pattern, you're going to go half as high. So you move one left, you go half as far from the y-axis, or from the y equals 0 line from the x-axis. Every time you move one to the left, you go half as far from the y equals 0 line from the x-axis. Move one to the left, you go twice as close again. Move one to the left, you go twice as close again. Move one to the left, you go twice as close again. You can keep doing that forever and you never get to the y-axis. Result is you have a horizontal asymptote. You never get to the x-axis. You keep seeing y equals 0 there, I want to say y-axis. You never get to the y equals 0 line. Your y value is never 0. You keep going halfway to 0. You can do that as x, doggone it, approaches negative infinity. And you never get to 0. But you get very close. Pretty soon, the curve will appear to merge with this line. But it never actually does. Okay. Another bit of arithmetic that I'm going to mention is what happens to 1 over x. So I'm going to move the board. Here, so I have this space to work on. Okay. Okay. Now, if x equals -2, y equals 1 over -2, which is -1/2. X equals -1, we get 1 over -1, which is -1. When x is -1/2, we get 1 over -1/2, which means 1 divided by -1/2, which is 1 times -2 over 1. Because when you divide by a fraction, you multiply by its reciprocal, and that gives us -2. Another way of understanding that, well, just a minute. Okay. If x equals 0, 1 over 0 is undefined. I think open math likes to say DNE does not exist. That's fine. Okay. 1 over 1/2 is 1 divided by 1/2 is 1 times 2 over 1, which is 2. Does that make sense? 1 divided by 1/2. Well, if you count by halves, you get 1/2, 1, 1.5, 2, 2.5, 3. Okay. 1/2, 1. There are 2, 1/2, 1, right? There are 2 1/2s and 1. So 1 over 1/2, it better be 2. Okay, anyhow, if x equals 1, you get 1 over 1, which is 1. If x equals 2, you get 1 over half, 1 over 2, which is 1/2. And then you get a corresponding graph. I don't know if you take time to sketch, because we didn't do it in the original class. Okay, now we're going to talk about composite functions a little bit. And one that I kind of mentioned earlier was that bell-shaped curve. So I'm just going to show you how that can be built up from a couple of toolkit functions. Okay, if f of x equals 2 to the x and g of x equals -x squared, then you have to accept that f of g of x is what you get if you replace this x with g of x. Okay, replace x with g of x, and this becomes this. Well, if you replace x with g of x, now at this point in class, I would say, write this down. Let me walk around and look. I recommend you stop and write down what you think it's going to be. If you replace x by g of x here, what do you get here? Well, hopefully you've written that down and you've written it down correctly and you've paused long enough to think about it. It's 2 to the g of x, because That's what this tells you. Okay, f of x equals 2 to the x. If x is replaced by g of x, 2 x here is replaced by g of x. Okay, you don't let the fact that there's an x inside of here confuse you with this x. The rule is simply replace x with whatever you see here. Do it blindly. Just do it by rote. Replace this x with whatever you saw here, okay? Now, you're not done because, of course, g of x has a formula. And it's 2 to the negative x squared. And as I mentioned earlier, that has a bell shape. It's very closely related to the visual bell-shaped curve you use in statistics. It comes as an easy composite of what I usually regard as the first two toolkit functions. There's another notation for this. This function has a name. Is f circle g. So you say f circle g of x is 2 to the negative x squared. F circle g is just a way of giving this a name. We talk about the function f circle g instead of the function f of g. It's just a little more concise to say f circle g. You might not think it is. You might want to stick with this. This means the same thing as this. But you're going to see that notation. And there's a good reason for it. Okay. Let me pause and see what I want to do for another example. I want to stay close to what I did in class. Well, okay, this is kind of interesting, but how do composite functions arise in the real world? Well, this is just a made up example. I don't think my numbers are going to be great, but you get the idea. If my driving speed is v in miles per hour, and the probability that I'm going to wreck is v squared. On the domain 0 less than or equal to v less than or equal to 200. If you're an ordinary driver, if you're going 200 miles an hour on the road that I'm thinking of, you're going to wreck and you're almost certainly going to die. So don't be doing 200 miles an hour. But unless you're a race car driver, you know how to handle good track, which I certainly don't. Okay, so let's just say that, okay, well, that's really not very reasonable because that gives you probabilities much greater than 1. If your probability is 1, that means you're certainly going to wreck. So I'm going to say that it's v squared over $40,000. Okay. So that when v is 200, that gets 1. Okay. That's kind of important, but you don't have to remember that. But if you understand probability a little bit, you understand what I just said. If you don't, that's okay. This is just an example of a composite. Okay, so let's suppose at time t, my speed in miles per hour is 4t plus 10. So, for example, if t equals 10, that's like 10 seconds, 4t is 40, add that to 10, you'd be doing 50 miles an hour after 10 seconds. Okay. You'd reach 72 miles an hour after 13 seconds. Yeah. Okay. So after 5 seconds, what's my probability of a wreck? Now, it's a little bit misstated because that would be like an instantaneous probability of a wreck. We could say probability per mile driven, okay? But that's I think you get the idea. Your speed determines your probability of a wreck in some sense. Okay, so after 5 seconds, what's the probability? Well, B equals 4t plus 10, and your probability equals b squared over 40,000. If t equals 5, b equals 4 times 5 plus 10 equals 30. And unless you're on a very tricky road, they have a very low probability of a wreck. But things can happen. And maybe it's a more complicated road, I don't know. Okay. Then the probability is b squared over 40,000, which is 30 squared over 40,000, which equals 900 over 40,000, which equals 0.0225. Now that's pretty high, so apparently we're on a pretty dangerous road. Okay, it's like almost one chance over, better than one chance in 40. So first 40 people go down this road at 30 miles an hour if they have this ability, as represented by these functions, somebody's going to wreck. At 30 miles an hour, hopefully it won't be too serious of a wreck, but you really get hurt at 30 miles an hour. Hit a brick wall, whatever. Okay, so this isn't a very realistic model, but it kind of depends on the road. Okay, well, P equals 20. You can check it out. 4 times 20 is 80. P is 90, doing 90 miles an hour. P equals v squared, which is over 40,000, which is 90 squared is 881, sorry, 8,100. over 40,000. You know, something's wrong with my numbers here. Yeah, I don't think so. Okay, well, at 90 miles an hour, you're going to divide this by this, and you're going to get my brain's freezing up. It's going to come unfrozen here in a minute. You're going to get 20.25. 0.2025, sorry. Okay. Something over a 20% chance of a wreck. Now I'm going to go ahead and erase this stuff on the left here so I can finish up. If you want to just calculate your probability of a wreck without having to go through two steps, calculating V and then calculating P, you could say that P is a function of, well, let's just give it another name. Instead of P, we'll call it Q, is a function of T, equals P of V of T. And what's P of V of T? Well, P of T is, or P of V is V squared over 40,000. So maybe I should have written that. P of V and V of T. Just to make sure that we're clear on this. Okay, so what's P of V of T? That's what you get if you replace V here with V of T. So that's V of T squared over 40,000. And what's that? Well, V of T is 4T plus 10 squared over 40,000. And maybe we want to expand that square, which is going to give us 16T squared plus 80T plus 100 over 40,000. And now, if you want to calculate your probability of a wreck after so many seconds, you just plug T in here. You want the probability of wreck after 100 seconds? Well, you can't use 100 seconds because if T is 100, you get 410, and you can't go 410 miles an hour. We're limiting you to 200 miles an hour, which is a pretty easy limit, okay? If T equals 40, then you get 40 plugged in here. Gives you the same thing as if you plugged in the 40 here to get 170. Squared 170 to get 28,900 and divided that by 40,000 to get 0.725, I think. Okay, I just did those off the top of my head. So go ahead and write them down and use your calculator and have a good laugh if I did it wrong. No, I didn't write this all out where you could see it. But there it is. Okay. Q of T is P of V of T. Using what we said, replacing V by V of T, we get this. And then V of T equals this. So here we have this. And then we do a little arithmetic, little algebra, and expand it. Then we get this formula. If you plug in 17 here, I think maybe you're going to get 7. Yeah, 725, and then 25 or something like that. Okay. You get a little fuzzy here. I've been doing this for a while. Okay. So if you plug 40 in for T, which is what I should have said, you get 170 here, 170 squared over 40,000, about 0.725, something like that. If you just plug 40 in here for t, you're going to get the same thing if I did all my symbols right. And that's kind of a big deal. That whole idea of a composite function. And also, you really want to understand composite functions because you have to be able to find rates of change of composite functions when you take calculus by taking what's called derivatives, something we're not going to do in this class, obviously, but something that you need this foundation in order to understand well.